a metre wide times by the thickness of our slab. So we're going to have two. So I'm going to start off with the data sheet. So I'm going to say we're going to call it section number 1. And you can see there's a little book. So that's a library. So if we were using I-beams or some other combination of steel, you could use that. But we're going to generate our cross section. So we're going to use the little section form here. So it gives us a whole lot of different options. So we're going to look at a solid rectangle. So its depth, we'll start with a 250 thick slab. And it's going to be a metre wide. So we're going to OK that. But I'm going to rename that so it makes a bit more sense. So I'm just going to call it 250 thick slab. We're going to OK that. So down the bottom, you can see the grey section number 1 is 250. But our beams are 600 deep. So this is where I'm going to use the left click and I'm going to select those members. So I've got all the beams in place. Now I'll go right click, properties. I'm going to change this to number 2. Alright, so number 2 hasn't been generated yet. So if I click the little I section, that gives me the section properties. And now I can build it straight from here. So again, it's going to be a rectangle. It's going to be a depth of 600. And a width of a metre. So we can OK that. So again, instead of calling it section 2, I'm just going to rename it. So a 600 deep slab. And you can see each of the different section properties, it uses a different colour. So it's very easy to see whether you've got the right section properties in the right place. Okay? So we can do, open the 3D render. And although it says wireframe, I don't know why it defaults to that. We're going to actually do a little render. Now this looks a bit unusual, doesn't it? If you look at the top of the slab. So if you're modelling this in a finite element analysis package, you would actually model it this way. But because we're only doing bending moments analysis, it doesn't matter whether the offsets are up or down. So Space Gas uses that wireframe arrangement, and we're going through the middle of that wireframe, so the middle of the 600 thick slab. So it looks a bit unusual, but it doesn't matter for this analysis purposes. Okay? So I'm just going to format that one. So we've got geometry and we've got our section properties in. The next thing we need to look at is material properties. So all of the slabs and all the beams are going to be 32 MPa. So we're going to call it material number 1. It defaults to steel, but it's got a library for us. So we're just going to go down to concrete 32. And these values are taken from the concrete code in terms of E value and phosphorus ratio, but notice there that the density is slightly higher than what we would assume. Okay, so we can change that to 24. That's what we want, 2.4 tonnes per cube. And okay, so now we've got our materials, and down the bottom it tells us materials concrete 32. So we've got everything set up now except for our loads. So the loads are pretty simple. So if we go left click and we can create a box, and we go left click down the bottom and go select members. So that's selected all the members. So now we can change those or whatever, but I'm going to go right click and that gives me a menu, and we're going to go down to distributed forces. Okay? So importantly at this stage, since you've selected all the members, I only want to input one load. So we're going to click the box down the bottom, or the dot down the bottom says apply loads to selected members as a group. So if you selected a whole lot of random members and wanted to have the same load on them, that's what you would select. So now it gives me one input screen here. So low case 1 we said is going to be called dead loads. So remember, we're only going to put in the dead loads, which are going to be in addition to the self-weight. So in that case, that's 1 kPa. So looking at direction up here, so Y is up and down. So we're going to put in a starting force and an ending force. in the Y direction. And so gravity's down, isn't it? But our positive Y is up. So do we put in a minus number there or a positive number there? It'll be minus. So we're going to put in -1 because that's our additional. And if you hit tab, it defaults over to the end. So you could put in a sloping load if you wanted to, as it's just going to be uniform all the way through. But at the same time, we can be clever about this. We can put in a live load as well. So using my example, I had -3 kPa. So -3, we can OK that. But it asks for load case titles. So if you're putting in a new load case, it'll ask for the titles. So I'm going to call that dead load, G. And we'll do the same thing for load case 2, live load.
Q.
Thank you. Okay. And so it's a bit hard to see because I've put them one over the other. But now if we come up to where it says all load cases, we can separate them out. So it's 1 kilonewton per metre. And up the top here, it's got what looks like a little piano next to the binoculars. So we can actually change that load scale. So I'm going to make it a bit easier to read. So that's a bit better. And then we can look at live load. So my loads are in pretty well, that's good. There's one thing that's missing. Remember how I said that space gas you can input self-weight? And so we need to actually put in a gravity load now. So we can come down to, oops, wrong one, to loads, and one says self-weight. So we're going to load case 1, and it does it in terms of G's, in terms of acceleration. So we just want -1, so minus being downwards again. We can OK that. And under the load case, it says SW. So now we're telling the computer, or the computer's telling us, it's included the self-weight in that load case. All right? Whereas if we go to load case 2, it doesn't say it there because we've only included it once. So we've got all of our loads in place. We've got a geometry in place. We've got materials in place, so that's all good. So the next step we need to look at is combination load cases. So this is where we can use combinations of load case 1 and load case 2. So we'd normally start those at 10. You don't need to. So we can say load case 10 consists of load case 1, and what's our multiplying factor for the dead load?
1.2.
1.2, beautiful. We look at load case 10, we've got to add load case 2 and 1.5. So now we've got a combination, and it says it's unnamed, so I'm going to change the naming of that. So I'm going to go down to load case titles, so load case 10. So you might choose to call it the strength or something like that. I'll just use that combination so I know which combination we've got. So now we can come up to do the analysis. So we've got our loads in, we've got our geometry, we've got our section properties. And I tend to do a non-linear analysis. I'm just going to analyse everything. So I don't change any of the defaults there. And it's analysed beautifully, which is good. Now if I come down to load case 10, I'm going to turn those loads off. So it actually generates for us bending moment diagrams and a shear force diagram. Okay? It's going down to, 2 decimal places. I don't really want to see that. So you can change that around. You can go to where it's got the number 2, and you can turn off nodes and other bits and pieces. But what I'm going to go to is more options. And I'm just going to say I want 1 decimal place. It makes the numbers a bit easier to read, and it rounds them up. So if we look at that distribution of shear force, it looks pretty good. That's what I'd expect. There's nothing funny about that. And the bending moment diagram through here as well. So the advantage of putting those extra nodes in at these locations here is when we're designing the slab, we actually need to design for negative bending moment. So negative bending moment is the top or the bottom in tension. Top, beautiful. So when we're looking at the maximum bending moment, which is at the middle of the support, so this one here, 126, our effective depth is actually based on the depth of the beam. So we can actually increase our effective depth, but we'd also need to check it at these two locations. You pick the maximum, so that in this case it's 57.6, and our effective depth is then just based on the slab depth, minus cover, minus half the bar. So you've actually got two bending moments to check, and you would choose the reinforcement that's the greater of those two, okay? So you might find that here's critical, you might find here is critical, all right? When we're looking at our positive bending moment, so positive is sagging, so we'd only be designing based on a 250 thick slab. So basically you've got three designs to do. So again, in this case, the worst case is going to be here, 45, the positive, but you've got the two negatives, those 2 points there, all right? And we choose out of those two negatives, we choose the critical area of steel, so the maximum area of steel, and then we design with that. But you might have different areas still here. So you can have different reinforcement. So they might both be N12 bars, so, but you can change the spacing on the bottom. So the spacing on the bottom reinforcement, because that's a smaller bending moment here, might be N12s at 250 centres or something like that. But for the negative reinforcement, you'd always expect a little bit more. But you can still use N12s, you just close up the spacing. So it might be N12s at 150 centres, for example. So the closer the spacing, the more steel you have per square metre.
Would that create confusion in the construction site?
No, because you're going to separate your bottom reinforcement as one plan, top reinforcement is another plan. So they'll put the bottom reinforcement in, and then they'll put the top reinforcement in. So they'll be looking at two different plans. So if you put it on the same plan, I agree, it might create confusion, but at the same time, the contractor might go, fantastic, lots of extra steel, I'm going to be paid lots of extra money, but the client's going to go, well, his competitor down the road did a similar building down the road for me, and it only cost me, 90% of what it's costing me here. I wonder why that is. So in terms of, you want to be efficient in your design, and because they're separate drawings, it's going to make it easy for the contractor on site to install. Okay. So the way that I was getting those bending moments, there's a little bending moment diagram here. You can turn that off. You can put the shear force on. So we'd only be designing our shear force at this interface here. We wouldn't worry about the maximum, because the maximums, again, we've got the bigger effective depth. So we'd only be designing our shear force in the slab for that 43.7. In fact, that one's slightly more, go to 49.5. So we're only designing that slab for shear once. And if you satisfy for 49.5 without any ligatures, and you shouldn't need ligatures in a slab, if you do, you've made a mistake, then basically that applies all the way through. Because if we're designing for the maximum bending moment, the maximum shear force, and we're satisfied those requirements, with concrete alone, it's all pretty sweet. We don't need to worry about looking at anywhere else. All right? The other thing which this will give us, and this is exaggerated, and we're going to be using this as part of stage 2, is it gives us the deflected shape. So there's two things to remember about this shape. One thing is we're using the uncracked section properties of the concrete. So we describe those as the gross section properties of the concrete. So our long-term deflection is going to be a lot more than this, but at least it gives you an idea. So we can use this and proportion it, so we can estimate what we think the crack properties are going to be, and we can proportion that deflection to suit. But don't worry about that, but I'm just showing you, so you can use this little icon over here, little deflected shape. If you're not sure which ones they are, just move the mouse over it and it gives you a description of what that button does. All right? So that's what you guys need to move on to next with your one-way slab. So the design we won't go through, but that's the analysis. And next week we'll go through the concrete beam as well. So that's a little bit more complicated, but along the same lines. So we've got to look at the geometry, set up the proportions, and then go from there. Is there any questions before I sit down?
you go through that